So maybe we should start now, Caro. Okay, here we go. Welcome to the Tipping Point discussion series. We're now on to installment 11 of this series. So the series now goes up to 11, and we're going to be talking today about atmosphere and cloud related tipping points. Before I start, I'd like to say that we started this series a little over a year ago, and it was started as a joint project between Earth Commission and Ames within Future Earth, and also the Safe Landings Climate's Lighthouse within WCRP, which I co-lead. And the idea was to explore tipping points in the Earth system, vulnerabilities, possible surprises, and to work through all the ones that we should be worried about, or that we possibly should be worried about. And we started this during COVID, and it's still going. And so that's where we're at now. I'd like to apologize to people in the US. Most of you are probably watching this on YouTube rather than live, since it's early in the morning, the day before Thanksgiving weekend. But that's okay. All of these can be found on YouTube through the confetti site at the WCRP or Future Earth, or just at the YouTube site. Okay, and these series, we've decided recently we're going to continue this series into 2023. So I'll mention that again at the end. If people have ideas for new events that they'd like to see, subjects we haven't covered yet, you'll have a chance to pop those into the chat with questions. Okay, we'll get started in just a second. And the ground rules are that we've got a chat and a Q&A. And if you have questions for the speakers, please put those in Q&A. If you have comments or other things, or you want to say hello or whatever, you can put that in the chat. But please put your questions in the Q&A. And what we will do is look at those at the end and have a discussion with both of the speakers. Okay. And so I guess we're ready to start. And the first of our speakers today is going to be Caroline Muller, who is at the IST in Vienna, where she's an assistant professor. She hasn't been there that long, I think maybe a year or so. She's rapidly building a group that are working on convective dynamics and possible ways that convection can organize. And so I would like to invite her to begin her talk.
Thank you very much. Thank you for the invitation, the organization, and this opportunity to share my work. And as Steve said, I will talk about the organization of convection. So I will carefully describe and define all the terms used. But here I just want to motivate a little bit the work. So I will talk about specifically the self-aggregation of convective storms. And that's one type of convective organization. And why did I want to talk about this for this tipping point series? Well, you can think of it as, the question is, if you have a state, a popcorn state, as Steve was mentioning earlier for the waiting for people to sign in, you have clouds that are distributed somewhat randomly in the atmosphere. You can think of it as a popcorn state. They pop randomly over the domain, the spatial domain. And then all of a sudden, there's a tipping point or a bifurcation that makes the clouds cluster together, aggregate together, and form spectacular organized systems. And so for obvious nice visual reasons, here I put a hurricane that's approaching Florida. It's Hurricane Floyd. That's one example of what we refer to as convective organization or clouds organization. And this is something that is important for many reasons. And so this is the talk of today. Before I start, let me acknowledge my collaborators. So Sarah Shamek, a former PhD student now at Columbia University, Benjamin Fillier, a current postdoc, and Sandrine Bonny, a collaborator from my former lab before I joined IST Austria. And also many collaborators, including Steve Sherwood, here present. So as I said, the talk is about cloud organization, and I want to spend some time defining what this is, what is the state, can we, I mean, something very visual. When we look at clouds from space, for instance, we can see them going from disorganized cloud distributions to organized systems. So I just want to show you some pictures and describe a little bit qualitatively what it looks like, give you some intuition or feeling about this field. And then in a second part, I will really dive into the physical processes that are involved in this self-aggregation of convection, this mode of organization that I work on. So first of all, for cloud organization, clouds are often spatially organized. This is the famous blue marble. This is a picture that was taken from an Apollo astronaut. And you can see here, and you're probably used to seeing such pictures, you can see that clouds are not randomly distributed over the planet. They form very distinct features, maybe some low pressure and cyclone forming. You have the mid-latitude or high latitude sort of comma-shaped clouds. And here, as I said, I think you are all used to seeing such pictures, but something that we often don't realize is that this is not something that we've had for such a long time. And in fact, as far as I know, the first picture from space was taken after Second World War in 46 from by a rocket. And you can see we can start seeing some clouds that have some large scale structure, but it's not very well resolved. And then from satellite, the first image is this one in the middle. I hope you can see my mouse. It's, I mean, I think you can all agree with me that the resolution is quite pathetic, right? And this is the 60s. And we had to wait until the 70s to have such beautiful high resolution pictures of the Earth. And in fact, I think this really, I realized this, that this is an exciting time to work on clouds. We are sitting on so much data now. We have so much available. And I realized this when I gave a talk, and one of my colleagues, she's a social scientist, she told me, well, you know, if you had been born at the time of Tintin on the Moon, the famous comics, I hope you know it, you would be out of business because there is no cloud. And so, by the way, if you don't know this, comics, I really recommend it. And indeed, if you look at the book, you see that when they're on the moon, they look at the Earth, there's no cloud. So I don't know if Hergé really didn't know that we could see clouds from higher altitudes, but it's telling you how little clouds were appreciated as an important part of our climate. But okay, so I'm a scientist, so I do my homework, so I reread the whole book. And to be fair, if you look inside, there are some clouds, if you actually look at all the drawings. But you can see, like, these are isolated clouds, scattered, randomly distributed, nothing like we can see on the blue marble. And now we can do things that are really spectacular. This is one example. This is a video that is put online every year. In fact, I highly recommend it. If you don't know what to do this weekend, please have a look at a year of weather. If you search it online, you have one every year. This is 2015 randomly picked. And what you're looking at are measures of high clouds. So it's a satellite measurement that is sensitive to temperature. If the temperature is very cold, they make it white. So just a word of caution, these are not exactly clouds. It looks like we're looking at clouds. We're looking at clouds that are high enough in the atmosphere so that their temperature is cold and they can be picked up by this satellite measurement. But still, if you look at the distribution, we see that it's very rich. You have a zone with sort of popcorn convection, small scale convection and clouds over pretty much in the tropics near the equator. Then in the subtropics at plus or minus 30 degrees latitude, it looks like there's a cloud desert. It's actually true for high clouds. There's not a lot of high clouds. If we could see the low clouds on the satellites, and there are other satellite measurements where you can see the low clouds, you would see that actually it's filled with low clouds, but there's no high clouds. By high, I mean like 10 kilometers altitude. So we see different characteristics at different latitudes. If you go even poleward, more poleward, you see that at high latitudes, we recover those comma-shaped clouds. These are actually clouds that are embedded in the high and low pressure systems that determine the weather at high, I was going to say our weather because I'm in Vienna, but I don't know where you all guys live. But anyway, in high latitudes, mid latitudes, this is the type of high low pressure systems that determine our weather. And the clouds are embedded in those systems, giving them the comma shapes. So it's very rich, very beautiful. We have lots of data. I really encourage you, if you like clouds, to not only take pictures of them from the ground, but look at satellite observations that are now freely available online. So this is a beautiful picture of clouds, but an equally beautiful picture, in my opinion, is this one. So here, what I'm showing is an anomaly of outgoing long wave radiation. So this is this satellite measurement that is sensitive to temperature. It's the long wave emission, sigma T to the 4, pretty much. So it's very sensitive to temperature. And here we're looking at the anomaly. So if there's a cold anomaly, it means that the emission is from a high altitude, a cold temperature. So there's probably a cloud. And if there's a warm anomaly, there's probably no cloud. And here we're looking at this as a function of longitude, that's the x-axis, and time going down. And the point here is that those, and this is in the tropics, so these popcorn clouds that we saw near the equator, you can see actually once you analyze a little more carefully the data, they're not randomly distributed only, it's not just popcorn convection, they have some large scale features. And those large scale features at what we call planetary or synoptic scale, so thousands of kilometers, they have been very well identified. In fact, there's a beautiful story behind this. In the 60s, Matsuno derived mathematically a very, very simple equation for the dynamics of the tropics, just mathematics. And he studied this very simple system and said, well, this system has waves, and those waves should have those properties. And then more than 30 years later, Wheeler and Kiladis wrote a seminal paper where they recovered those waves in observations. So it's one nice example of mathematics works, and simple models can give you a lot of information qualitatively, but also quantitatively to understand our atmosphere. And so here, this is what's shown here as envelopes, different waves. So you have the Kelvin waves, you have the equatorial Rossby waves. These are different waves that are in this simple model of equatorial dynamics of the atmosphere. You also have a large packet called the Madden-Julian oscillation, which is a talk in itself, but it's one mode of organization of clouds. And these are, I would say, fairly well understood in the sense that we have a mathematical model that matches them, at least qualitatively. There are still research questions there. But what I want to emphasize is that in addition to those synoptic or planetary thousands kilometers organizations, you have very often some potatoes of clouds, I don't know how to call them. Actually, I know they're called mesoscale convective systems. So these have, you see the scale separation. These are more at 100 kilometers or hundreds of kilometers. And clouds tend to organize at those smaller scales. So I say small, but actually they're not that small. So this is a famous picture of a mesoscale convective system. The point is that it lives longer than an individual cloud, and it spans a larger surface than individual clouds that you can see a little bit below this huge anvil cloud. And here I'm showing one that's forming over Austria, where I'm now, but that's random. I found this one online. And you can see that the clouds, what we're discussing at the beginning, the clouds that are somewhat randomly distributed, here we see temperature. So again, the colors are a proxy for how high the clouds are, right? So cold temperatures mean high clouds. And you see that those randomly isolated, randomly distributed clouds cluster together and form this huge mesoscale convective system. This is the type of scales that I'm interested in, the mesoscales, and the type of organization that I'm interested in. And particularly, one thing that has triggered quite a lot of excitement in the community recently is the study of the clustering of clouds in idealized settings. And this is what I'm illustrating here. This is typically the tools that I would use in my research. It's a cloud resolving model, meaning the resolution is about kilometric. So you resolve the convection, the movement of air, and the cloud formation that are associated. And at the top, you have a typical idealized simulation that we call radiative convective equilibrium. Basically, it's very idealized. The Earth is flat. The sea surface temperature is homogeneous. It's 300 Kelvin everywhere. There is no large-scale forcing, and the domain is doubly periodic. So something living here is coming back on the other side. And typically, such radiative convective equilibrium simulation reaches what we call popcorn convection, so the randomly distributed. Now, under certain circumstances, there is a tipping point or bifurcation to a state where the clouds self-aggregate. And this is what's shown at the bottom. One of those conditions under which that happens is a large domain. The only difference between those two simulations is indeed the size of the domain. And so here you see that the convection and the clouds are distributed very differently. They're all clustered in a fraction of the domain. And this is very spectacular, this bifurcation to the aggregated states. This has been called self-aggregation. And you can define it as an instability of the disorganized radiative convective equilibrium popcorn state. And this is not an exhaustive list of all the papers that have come out on this phenomenon. So the rest of the talk, I hope the introduction was clear. Clouds, if I can summarize, clouds organize at various scales. At mesoscales, it's still quite mysterious how they do. And one, I think, promising route or avenue are those idealized simulations. So let's analyze them and see what are the processes involved. And here I'm going to present results that we recently published, actually with Steve Sherwood as well, in a review paper for the annual review of fluid mechanics, where we discuss the theoretical models or conceptual models that have been proposed to capture the physical processes leading to this self-aggregation. So namely, there's 4 processes, and I will go through them one by one. They're illustrated on this schematic. So the first one is the radiative cooling in dry regions. When clouds tend to cluster, they have an environment that becomes very dry, that cools very efficiently radiatively, and that tends to generate a circulation that enhances the clustering. So let me show you some evidence for this. If that was not clear, I'll be a little more precise and slower now. So here, the first thing we did, actually 10 years ago, when I was still a postdoc, the first thing we did is take those idealized simulations that we saw and remove some of the feedbacks, right? It's simulations. We can play God and go inside the simulation and change whatever we like. And so what we did is we thought, what are the feedbacks that can lead to this self-aggregation? And there are several candidates. So one of them is surface fluxes, right? The fact that surface fluxes are different when there's a cloud or when there is no cloud. And so that could lead to enhancement of clouds and clustering. But if you homogenize surface fluxes, you still have some sort of aggregation. Or it could be radiation. So I haven't talked too much about radiation. I mentioned it a couple of times. Basically, any parcel of air in the atmosphere cools radiatively, emits radiation to space or interacts with the surface or lower levels. And this cooling, this rate of radiative cooling is a function of its temperature, as we discussed, but also of its water vapor content, of its cloud amount. And thus the amount of radiative cooling is different in clouds and outside clouds. And maybe that's this difference that is responsible for the aggregation. And it turns out to be true, and more specifically, not in the short wave, so the solar radiation, but in the long wave, the thermal radiation. If you homogenize the long wave, you lose the aggregation. So now the question is, why is long wave interactive radiation crucial? Well, we believe it's because it generates this radiatively driven circulation that I showed on the schematic. And let me make it a little more quantitative now. So here on the left, I'm showing the rate of radiative cooling in Kelvin degrees per day as a function of height and moisture. So on the right, I've averaged all the moist columns. On the left, I've averaged all the dry columns. And you can see here that the radiative cooling is different in moist and dry regions. And specifically, there is a strong cooling at low levels below 2 kilometers or so in the dry columns. And now on the right, I'm showing the same plot in height and moisture space, but I'm showing moist static energy, the energy relevant for moist convection. And you can see that if you cool the radiative cooling in dry regions, if you cool the air, it's going to sink. And here, in fact, the black contours are stream functions. So you do have a sinking circulation in the dry columns. And then you have a near surface flow from dry to moist column. Now, if you look at the energy in the background, it's taking high energy from the dry columns and it's giving it to the moist. So you're taking money from the poor and you're giving it to the rich. That's a positive feedback, right? It's strengthening the clouds where they are. And this is actually, in essence, let me just pause for a second. All those four feedbacks, the idea is the same. These are feedbacks that will favor clouds where they are. So if you have a cloud forming in one location, this feedback will favor the next cloud in this same location, and that gives you the clustering process. Okay, and here's the idea. This circulation generated by the cloud will favor clouds in the moist columns. And just to, I mean, this moisture height space is not necessarily easy to visualize. So at the bottom, I'm showing it in 3D. It's basically a near surface flow going from dry regions to moist regions. It's bringing moisture and energy towards the clouds, and it's maintaining the clustering. So in fact, if you measure the strength of this shallow circulation in different simulations that aggregate at different speeds, so here, this is some aggregation index. I haven't defined it and I won't, but just believe me, this is measuring the strength of aggregation as a function of time. These are different simulations that aggregate at different timescales, more or less fast. Now, if instead you plot this aggregation index as a function of this shallow circulation, you can see that all the curves collapse on top of each other. So that means that the aggregation evolution is entirely explained by the strength of this shallow circulation from dry to moist regions, which is driven by radiation. And this has been formalized now in a simple theoretical model of water vapor perturbation stability analysis, right? And the idea is that you have a water vapor distribution, you assume some perturbation, a little moist here, a little dry here. And the key question is, does it go back to being homogeneous, or does the moist region become even moister? So does the initial perturbation get dampened, or does it grow? And for some conditions, you can make it grow, which means that you have this self-aggregation feedback captured. Okay, I hope that's clear. That's for the first one. And the second one is turbulent entrainment at the edge of clouds. Again, it's always the same idea. Clouds favor clouds in their neighborhood, if you want. So if you have a cloud somewhere, you will favor the next cloud to be at the same location, and that's a positive feedback on the clustering. So how does turbulent entrainment work? As the cloud is formed, you have lots of entrainment at its edge, and here I have a little schematic from a website that I really am fond of. It's called the COMET program. Again, if you don't know what to do, so this weekend you check a year of weather, but next weekend you can check the COMET program website. They have lots of online courses. It's entirely free. You just have to sign up with your email address. And they have lots of courses on different aspects of meteorology and atmospheric science. It's really well made. I use a lot of their schematics in my talks and courses. Okay, end of parenthesis or ad break. Here, what I'm showing, what I want to illustrate is the life cycle of a typical cloud, single cell. And so here, at the beginning, you have some sort of upward motion that's triggered, so by convergence or heating the surface, whatever makes the air light, it goes up. And as it goes up, it keeps going. If it stays lighter than the environment, it keeps going, it's lighter, until it reaches what we call the equilibrium level, where its density matches the environment, and then it spreads horizontally as an anvil cloud. And in the cloud, there are interesting microphysical processes that I'm not going to talk about, but again, you can check the COMET program if you're interested. I'm happy to give you references. And the cloud droplets that are very small, they become bigger. And as they become bigger, they start to fall and precipitate. And at the end of the cloud, the precipitation cools the air, it's latent cooling, and this generates downward motion. The air is cooler, it's heavier, now it goes down, and it kills the cloud. It kills the upward motion that started the cloud. So this I call the cloud suicide sometimes. You need upward motion to start the cloud, and then the eventually the downdrafts generated by the latent cooling associated with evaporation of rain will kill the cloud. Okay, so that's the life cycle of a cloud. I need this. Now, how about the entrainment feedback on aggregation? So you can see, if you look outside your window, if you've ever seen a cloud grow, you can imagine that there's a lot of turbulence at the edge of the cloud. Now imagine if there's a cloud somewhere, and then there's a next cloud coming, it's going to entrain air that the previous cloud has moistened, and so that's going to help it stay buoyant. On the other hand, if a cloud goes in a location where there was no cloud before, the air will be drier, and so it will entrain dry air, and that will tend to kill it, to kill the buoyancy, to reduce the buoyancy. And so it's a sort of positive feedback of clouds on themselves. If you have a cloud, you moisten the environment that favors the next cloud to form. And consistently, if you increase the entrainment rates in simulations, you favor aggregation. And this is something also that has been captured in a simple theoretical model that I'm showing here, or showing. I'm just going to give you the big picture, and hopefully it will motivate you to go check the literature. So here, it's an equation for atmospheric humidity, right? QV is the water vapor specific humidity. It's integrated vertically. So it's the whole water vapor in each atmospheric column. And you can write its temporal evolution as the negative of derivative of a potential. And this, I'm not going to go into details, but this includes sources. If you have convection, you moisten the column. Sinks, if you have subsidence, for instance, with radiation, you have a drying, and you have some horizontal diffusion due to entrainment and transport. Now imagine if V, this potential, has a minimum. Now, if you're in a place where your humidity is larger, so you're somewhere, or V on the right-hand side, then dIdt is negative, so you tend to go back to the minimum. Similarly, if your humidity is such that you're a little bit on the left, a little bit lower than the minimum, then from this equation, dIdt is positive and you go here. So the minimum is an attractor for the model. And this is something that is reproduced in this numerical simulation of their simple model, and you do get some sort of aggregation with the multiple equilibria, so two minima. Okay, and very briefly, the last two ones, so the evaporation-driven cold pools, we mentioned this in the life cycle of the cloud. At the end, the cloud suicide is when you have this downdraft, this cold air from the evaporation of rain, and this cold air reaches the surface and it spreads. And this is what I'm showing here in idealized simulations. The colors at the bottom are near surface humidity, and the gray surfaces are clouds as usual. And you see at the end of the life of the cloud, you have this dry, cold air that's spreading. We call them cold pools. What happens is that sometimes two cold pools merge, and when they merge, they create a new cloud. So it's again the same idea that if you have a cloud and another cloud, through the end of the cloud and the cold pool spreading, they will generate another cloud in their neighborhood, and that will help the clustering. And this is something, again, that has been worked on by Jan Harter and his group for a while now. They have a series of very nice papers on this, where they can capture this also in a conceptual model and high resolution simulation. Okay, and I will, then skip this and go to the last one, which is the wave emission. And this idea was put forward by a seminal paper by Brian Mapes, where he argued that if you have a cloud, you tend to excite different waves. And one wave is the deep barotropic wave. So it's a wave that tends to correspond to the deep latent heating of your cloud. And this deep wave propagates fast. And then at the end of the life cycle of the cloud, we said there's warming aloft, but then there's latent cooling as the rain evaporates. And this is the first baroclinic mode, and that tends to propagate slower. And what happens is that this first baroclinic cools the air, so it tends to make the atmosphere more unstable, and it favors clouds and convection. Whereas the other mode, the deep mode that goes faster, tends to stabilize the atmosphere. So the bottom line is that if you have a cloud, you tend to stabilize the further distances, but you tend to favor cloud to destabilize your neighborhood. And again, that's a positive feedback on cloud clustering. And this has been also formalized in a simple model. So I think I went a little bit over time, sorry about this, but I will conclude now. I hope I've convinced you that convective organization is exciting, and there's a lot of different feedbacks, and these are just a few of the papers that talk about this. And in recent years, our improved fundamental understanding of this has allowed us to capture this in simple theoretical models, as reviewed in our recent papers. Thank you very much for your attention.
All right, thank you, Caroline. That was a very impressive and really well explained deep dive into cloud organization processes. A lot of fascinating stuff and great movies. We'll have in the Q&A, we'll have to bring all that to bear on climate, and I think the next speaker will help move us in that direction. And so that's going to be Professor Rodrigo Caballero, who is at Stockholm University. He's been there since 2011, and he's a bit unusual in that he's an atmospheric dynamicist who has worked largely on paleoclimate. So over to you, Rodrigo, if you're ready. There we go.
Okay. So thanks so much, Steve, for the invitation to present my work here and for your nice introduction. So yeah, I'm going to be talking about superrotation, shifting gears quite considerably from the very interesting material, cloud-related material that Caroline was talking about. I'm going to talk about superrotation, which is a somewhat exotic topic discussed, of interest to geophysical fluid dynamicists and of obvious relevance to planetary atmospheres. I'm going to try and draw out the connection here, or the possible relevance of superrotation to Earth and its possible connections to clouds and to climate. And I'd just like to acknowledge then the people I've worked with on this topic over the years, Matt Huber at Purdue, who I learned a lot about paleoclimates from, former PhD student Henrik Carlson, and then current undergrad and Freddie Boucher at in Lyon in France. So let's start with a definition then, so we're on the same page. So superrotation is defined as a state in which the atmosphere at some point, at some latitude, is rotating faster than the solid Earth itself at the equator. Okay, so the angular momentum of a ring of air at some latitude phi is expressed like this. So there's a solid body component connected to the solid body rotation omega, and a relative, component connected to the relative motion, so to the wind. And and this is the equatorial solid body rotation value, and so that means that the wind needs to be bigger than this quantity here. Okay, and in order to be in superrotation, and so that this particular profile is shown here by the dashed line. And so if the wind anywhere is the zonal mean wind is anywhere greater above this dashed line, then you're in superrotation. And as you can see for Earth's atmosphere, this is strictly not true. So the Earth's atmosphere very carefully avoids being over the superrotation threshold near the equator, okay, and in fact everywhere else. So it came as a great surprise when people started to look at the atmospheres of other planets, in particular Venus, to realize that those atmospheres could superrotate. Okay, so it's been known since the 70s that Venus superrotates, and we have better data now. And so the equatorial wind in Venus is like 80 meters per second, so really strong. Titan, which is a moon of Saturn, also superrotates. In fact, there was a sonde that went into Titan's atmosphere some years ago, and they actually measured a profile of wind on Titan, and this is shown here. So near the equator, the winds go up to about 40 meters per second. Why was this a surprise? Well, for a start, it's different from Earth as we know it. So it requires some explanation, and that explanation requires some interesting behavior by tropical waves in particular. Okay, so this gets a bit technical, but I hope I can give you the big picture here. So the zonal mean momentum budget for the for an atmosphere, for a rotating atmosphere, is shown here. Okay, so bars indicate a zonal mean, and so the budget contains three terms essentially. There's a mean flow term, which is in the tropics. It essentially describes the Hadley cell, so a sort of a meridional vertical overturning circulation. Okay, then there's an eddy term, so primes are deviations from the zonal mean, and so there is a term contributed by these eddies, and then there's just viscosity, which somehow captures the behavior of smaller scale eddies. Okay, the large scale eddies here, we think of them as being essentially large scale balanced circulations, okay, geostrophically balanced circulations, and these are smaller scales. Okay, so it's been known for a while that the mean term and the viscosity by themselves can't generate superrotation. That's something popularly known as Hyde's theorem. Okay, so superrotation must be generated by the effect of eddies. Okay, and in particular, it requires up-gradient momentum fluxes by eddies. Okay, so eddies have to pile up momentum onto the equator, as kind of shown here in this cartoon. Okay, and that tendency of these tropical eddies to pile up momentum onto the equator then is contrasted by the tendency of the mean circulation and of exotropical eddies, in fact, to remove momentum from the equator. Okay, so it was a puzzle back in the 70s to understand how eddies can converge momentum, so go, transport a quantity momentum up the mean gradient, because we usually think of eddy transports as being diffusive to a first approximation, and so they will transport things down gradient. Okay, so that is a whole chapter in geophysical fluid dynamics, and we now, well, the state of the field is that we now feel that we have a sense for how that works. I won't go into all those details, but let me just say that if you have waves that are generated in a certain region, like in the tropics, and which propagate away from that region, then they will naturally tend to converge momentum onto that region. Okay, so it's really tropical eddies generated near the tropics, which propagate away from the equator, that converge the momentum, and then other eddies generated in the mid-latitude will try to draw momentum away from the equator, and the mean circulation will also take momentum away, because, as you can see, the mean circulation will be bringing up low momentum air from near the surface and taking out higher momentum air, and so it will act to damp the momentum here. Okay, so the whole problem is an interplay between momentum convergence by tropical eddies and momentum divergence by the mean circulation exotropical eddies. Okay, so what kind of tropical waves are we talking about here? And here I make some contact with Caroline's talk earlier. Okay, so the first suggestion back in the 70s was with vertically propagating gravity waves. I won't talk about that so much. That's probably not so relevant for Earth. More likely relevant for Venus, but that's a story for another day. Instead, I'm going to focus more on these more geostrophically balanced large-scale waves. Okay, and there are several types of these waves that are known to be able to generate momentum convergence on the equator and potentially drive superrotation. And one is the thermally forced Matsuno-Gill type stationary waves. These are relevant to the Earth because on the equator you have a zonal heating contrast between the warm pool in the Western Pacific and the cold tongue in the Eastern Pacific, and that does drive stationary waves, tropical stationary waves in the atmosphere that do show momentum convergence onto the equator, and by themselves would actually drive superrotation on Earth. But on Earth, we're in a situation in which the divergence is, by the mean circulation in particular, is stronger, and so we don't observe superrotation on Earth, but we could if the divergence were weaker. Okay, Another type is the Madden-Junior oscillation that that Caroline already mentioned. So that's a large-scale traveling wave, okay, in the tropics, whose nature is, interesting. And finally, more recently, there's been a lot of interest in this topic of Kelvin-Rossby instability. Okay, so there's a sort of family resemblance amongst all these three types of waves in that they all comprise essentially a Kelvin type mode near the equator and then a Rossby type mode off the equator. So you have high pressure, these are usually sort of planetary scale waves, and they come in as sort of, there's two dipoles. You have high pressure here, high pressure to the west and low pressure to the east, okay? And right on the equator, you have a sort of Kelvin type component, okay? And it's the phasing between the Kelvin component and the Rossby component that gives you this tilt, which is responsible for converging momentum onto the equator, okay? And what has been realized recently and is drawing some attention is the fact that, in fact, there may be an unstable interaction between the Kelvin and Rossby, equatorial Rossby wave components that can lead to self-amplifying modes that have precisely this kind of structure, okay? So that's a sort of an active area of research in this field right now. Okay. So I guess this seminar series is about tipping points, so I should say something about tipping points. So the question is, can you imagine the system transitioning to superrotation as a tipping point, or more technically known as a subcritical bifurcation? Okay, that is a situation in which, with a given set of parameters, you have two stable equilibria, and you can transition between them by for instance, noise can drive you from one equilibrium to the other, or if you change the parameters, one of the equilibria becomes unstable, and so you can jump to the other equilibrium, okay? So for this particular question of superrotation, essentially, if you have the forcing due to momentum convergence by tropical eddies and the damping due to divergence by the other terms, if either or both of them depend on the mean wind itself in some nonlinear way, then yes, you can get into a situation in which you have multiple equilibria, okay, and possible tipping points. And in fact, there have been a whole number of papers over the years that have proposed different mechanisms by which you can generate such multiple equilibria, okay? Now, all of these have been demonstrated in sort of reduced complexity models, okay? The most sort of closest to realism is this recent work by Pablo Zurita-Gotor and Isaac Held and others, in which they have a full 3D dry dynamical core, which exhibits such a bistability, okay? But it hasn't, to my knowledge, it hasn't been demonstrated in any full complexity climate model with moisture and clouds and realistic radiation and so on. Okay, so that remains kind of an open question. Okay, I'm going to switch gears now to talk about superrotation in an Earth-like simulation, okay? Or in particular, a transition to superrotation, which occurs when you make the climate really hot, okay? This first sort of, I got interested in this topic when my colleague Matt Huber, who has been working on warm paleoclimates in the deep past, in particular the Eocene, was doing a set of full complexity simulations for the Eocene using very high levels of CO2. And he realized that it was superrotating. So he drew my attention to this, and then we looked at it in more detail and did a lot of really fun work, I must say. It's been an interesting chapter in my research career. So here's a sort of simple representation of this transition. So I'm showing you some simulations with CAM3. This is a GCM that has, moisture, clouds, the whole, it's full complexity in that sense. I'm showing you for simplicity the aquaplanet version of this. So there are no continents here, just a slab of ocean that only has a thermodynamic role. Okay, whoops. And so what I'm showing you here is the shading shows the zone of wind, and this is for, you know, a cold state, relatively cold state with 280 ppm of CO2 in the atmosphere. And so you see a very conventional circulation with, you know, Hadley cells as we see them, very weak to negative winds on the equator and the sort of subtropical mid-latitude jets. And the white line here shows you the eddy kinetic energy. So it shows you that most of the eddies, most of the waves in this simulation are in the mid-latitudes, okay? So you have a strong updraft in the Hadley cell and strong mid-latitude eddies that are making superrotation impossible in this case. Now you take exactly the same model and you switch the CO2 up to, you know, a very high value. This is 4 doublings with respect to this value. And you see a completely different picture with a much weaker Hadley cell, wave activity mostly in the tropics. Okay, there's some in the extropics as well, but it's mostly in the tropics, and pretty strong superrotation, you know, in excess of 20 meters per second on the equator. Okay, so so that's interesting, and so we spent some time trying to understand what, you know, how this works, and in particular, the first thing we looked at was, you know, how does this, what kind of waves are we talking about here? What is this wave activity that arises in this warm climate and drives the superrotation? Okay, and what we found when analyzing those waves is that they are basically something that looks a whole lot like the MJO, like the Madden-Julian oscillation. So they are wave number 1, planetary scale waves, with a classic structure with, you know, off-equatorial Rossby gyres and an equatorial Kelvin component, and which propagates eastward at a phase speed of about 30 meters per second, which is fast compared to the observed MJO in the current climate. But on the other hand, these waves are embedded in a strong superrotating wind, which is advecting them eastward. Okay. Okay. And then this figure gives more of an overview of how you transition then into the superrotating state. This was to look for evidence of sort of, you know, subcritical bifurcation or tipping points. And the answer is that it looks more like although we don't know for sure, but it looks more like a smooth transition into superrotation. Okay, so the left panel here shows you the wave amplitude on the equator. And you can see that the wave amplitude increases fairly gradually, okay? And as the wave amplitude increases, you tend to increase the superrotation also, you know, proportionally to the wave driving, okay? By the way, the different colors here are different configurations of the model. So we tried aquaplanet, we tried Eocene surface conditions, and we tried modern surface conditions, and they all behave in a qualitatively similar way, although with, you know, quantitative differences. Okay, I think that's all I want to say about this. Oh yes, to address the question of tipping points, we actually tried starting from one of the hot simulations and then as an initial condition, and then reducing the CO2 to see if we would follow a different branch, but we don't. When you do that, you actually follow the same branch. So it looks like, at least in this case, it's not a tipping point. The transition from, you know, from subrotating to superrotating is not a tipping point, but more of a smooth transition. Okay, there is a gap here. So each dot is one doubling of CO2. Okay, so this is pre-industrial CO2, and then each dot is a doubling from pre-industrial. And you see that there's a large gap here. So when you do this doubling, you get a very large increase in surface temperature. Okay, so that makes it look a bit abrupt. But this, in fact, is connected more to a change in climate sensitivity, which is what I'll discuss next. Okay, because one of the really interesting things that we realized here is that, precisely as I said before, the climate sensitivity of these simulations increases dramatically at the same time as you transition to superrotation. Okay, so here is the climate sensitivity for these simulations, in particular the ones with the Eocene configuration. Okay, and this is the climate sensitivity across each CO2 doubling. So this value of CO2 shows you the base value. Okay, so this dot here refers to the climate sensitivity in going from 280 to 560 ppm and so on. Okay, and you go at cold temperatures, low CO2, you have a sort of fairly standard climate sensitivity of about 2 Kelvin per doubling. And then as you get to this point, or this transition here, or this doubling here, which is precisely the one that takes you into the superrotating state, then the climate sensitivity is 6 Kelvin per doubling. Okay. And further analysis shows that that is mostly due to shortwave cloud feedbacks. Okay, so this is a kind of complicated plot with all the feedbacks drawn in, so you can ignore most of them. You can just look at the total cloud feedback, which is this red line, and you can see that when you get to this doubling here, the total cloud feedback increases rather dramatically. And if you decompose the cloud feedback into a shortwave feedback and a longwave feedback, which is the dashed red and the dotted red, and this is the longwave feedback, and that, doesn't change so much, whereas the shortwave feedback actually changes sign, going from negative to positive at that transition. Okay, and if you look at the clouds themselves, okay, and I'm showing you again the results from the aquaplanet simulation here for simplicity, because it just shows the result more obviously. You can see that when you go into this very warm climate, the clouds in the tropics, become a lot less abundant than they are in the cold climate. Okay, and that includes high clouds right on the equator, middle clouds on the equator, and also low clouds in the subtropical region. Okay, all cloud types tend to get a lot less prevalent as you go into this warm climate. Okay, the fact that you have less high cloud is, plausibly connected to the fact that you have a much weaker Hadley cell in this situation. Okay, so you have stronger or weaker updrafts here in the equator. And the disappearance of low clouds could also be connected to the same aspect of this simulation, which is this weakening of the Hadley cell. Okay, although the truth is that we haven't actually pinned down the exact connection between these changes in the circulation and the changes in cloudiness. That remains an open topic here. Okay. Okay, having said that, let me move on to this issue, which is raised by the results I just showed you, which is actually a point that was made by Ray Pierre-Humbert, actually in the commentary to the paper on climate sensitivity that I was discussing previously. Okay, so you can imagine that the transition to superrotation actually entails a transition or a tipping point in Earth's energy balance. Okay, so the idea here is that as a function of surface temperature, you have a certain behavior of the outgoing long-wave radiation, which is shown by this red line here. Okay, as you increase CO2, this red line will shift to look more like these dashed lines. Okay, and it's precisely to come into equilibrium with this smaller OLR that you need to increase the surface temperature. Okay, and the yellow line shows you the absorbed insolation. Okay, which in this case depends on the surface temperature. Let's hypothesize that it depends on the surface temperature, because as you increase surface temperature, you transition to superrotation, and the superrotation causes a loss in cloudiness, and therefore an increase in the absorbed insolation. Okay, so if you do have the behavior schematized here, you can get into a situation in which you have tipping points, and as you increase CO2, you will suddenly transition to a state that has much fewer clouds and you know, as you reduce CO2 below this point, you will have a sudden transition to a much warmer climate and a much higher climate sensitivity. Okay, and this mechanism doesn't necessarily require a bifurcation in the superrotation itself. Okay, it could happen with this bifurcation or a tipping point in the superrotation itself, but even if the superrotation is a smooth transition, it could still drive a tipping point in the energy balance as shown here. Okay, this hasn't been demonstrated anywhere. It remains a speculation, but I thought since we were asked to explore the research frontiers, I thought I'd put it out there. Okay, and finally, just as a closing point, I don't know how I'm doing for time. Yeah, okay. Just very, very quickly, another possible climate implication of superrotation is that if superrotation were to come all the way to the surface, so as I showed you before, the superrotation in all the simulations we've seen so far is really confined to the upper troposphere, okay? But if you had superrotation coming all the way to the surface and driving, you know, mean surface westerlies on the equator everywhere, then that would radically alter the ocean circulation in the tropics, and in particular, it would presumably destroy the east-west temperature gradient on the equator, and therefore remove the possibility of El Nino Southern Oscillation type of variability and put you in a sort of permanent El Nino situation. Okay, that's an idea that was raised in a paper by Rapier Humbert as well, and in more detail by Zipperman and Farrell. And recently we had a paper in which we looked at that in more detail to see if it was actually possible to have superrotation come to the surface in a full complexity GCM. And the answer is yes, it can happen, but it requires a very extreme parameter setting, which is unlikely to, well, it's unlikely to happen anytime soon. You need a very extreme climate for it to happen. And with that, I'll come to my summary slide. Just maybe in the interest of time, since I'm running a bit short here, I'll just leave them there for you to look at. And there are some open questions here that I pointed out that may be of interest for some of you to consider. In particular, maybe one point I can make is, you know, it's still unclear whether the transition to superrotation causes cloud clearing, or whether the cloud clearing, so in other words, the drop in cloud abundance when you transition to superrotation, if it's causally linked to superrotation, or if it responds, or if it's due to other mechanisms. Okay, in particular, Tapio, Schneider, and others had a paper in 2018 where they discuss mechanisms by which subtropical clouds can dissipate at high temperatures, which is entirely independent of dynamics, actually. Okay, so how these two things go together remains a kind of an interesting question. And with that, I'll close and thank you for your attention.
Okay, thanks very much, Rodrigo.
Should I stop sharing, or?
Yeah, I guess stop sharing. And yeah, so that was also a great talk, really, really clear, and showing some exotic things that maybe not all of us are thinking about, even including in the tipping point community. Even if, as you say, superrotation may not be a tipping point in the mathematical sense, it still looks like something that might matter if it happened. So as I threatened earlier, I'd like to, first of all, before I say that, please put your questions in the Q&A, audience, if you've got questions. There's a couple there now, but I'll wait for some more to show up. And while that's happening, I wanted to go back to Caroline and ask, do you think that this organization that you showed could explain or have anything to do with some of the results that Rodrigo was talking about, or do we expect this to change in a warmer climate? What do we know about the possible climate role, or how this might change in a warmer climate?
Yeah, so that's a very good question. In fact, I was thinking about this during Rodrigo's talk as well. So the thing is, I insisted on those mesoscales, like hundreds of kilometers. And if you look at climate sensitivity in climate models, the main sensitivity comes from, or the main uncertainty, sorry, comes from clouds. If you look at how different the different models are, the intermodal spread in climate sensitivity estimates, it comes from clouds, but it tends to come from low clouds. Those low clouds in the subtropics that reflects the solar radiation and cools the surface. So that's helping cooling our climate. But this organization at mesoscales that I talked about at 100 kilometers, that's the resolution of a climate model. So a climate model every 100 kilometer or so has one value of cloud amounts, wind, pressure, temperature, etc. So they don't have any way of having this organization of clouds at mesoscales, going from individual kilometer scale to mesoscales. And so we don't know, from climate models, we don't know how this organization will change, and we can't address this question with climate model. What we can do, there are several avenues. Either we do idealized higher resolution simulations to see how this organization changes with temperature, how it responds to climate. And it's a hard question. Alison Wing has a review paper on this. The answer is typically aggregation is favored at warmer temperatures, but it is somewhat sensitive to the details of the models. So I think there's no definite consensus. It's a hard question that many people work on, including some participants. I recognize some familiar names. And then the impact on climate. So a key question is, how does this organization change with warming? And why is that important? Because it could contribute to climate sensitivity in the following sense. If you have more clustered clouds, you free a lot of cloud-free area around them, and that will lead to strong long-wave cooling to space. And so technically, it could also cool the surface and help mitigate global warming. This is the sort of the so-called iris effect. Again, it has been studied. It's a very important question. I don't think there's a definite consensus yet, but there have been people working on this. And I mean, yes, if you have more clustering, you have more long wave cooling. So that tends to be a negative feedback on global warming, but you also have less cloud area. And so you have also more shortwave coming in. So you have more warming from shortwave and more cooling from long wave. And the question is, which one wins? And I don't think that's an answered story. So if I want to summarize, the clustering is important for climate sensitivity because it impacts the radiation imbalance, the energetics. But we can't use climate models, and it's not present in current climate models.
So that sounds like a, I don't know.
Well,
that's
it's
fine.
not just an I don't know. I mean, there have been a lot of work. So there are things we can say. It increases the long wave cooling, it helps. But how exactly organization will change with warming is difficult. And one very, very promising avenue are actually the new high resolution climate models that are being developed. Mainly, the effort is mainly led by Europe and the MPI in particular. And people look at this, how organization changes in those global simulations, so realistic, but with a resolution fine enough to have organization. And these simulations are, I think, a very, very important breakthrough.
Okay, great. I'd like to go over and ask a related question to Rodrigo. You talked a lot about wave transports. And actually, both of you, Caroline, you showed a Hofmüller diagram with all the different tropical or convectively coupled waves. But we know that GCM, at least I think most GCMs and particularly CAM, do not simulate these waves or MJO phenomena very well. What does that mean for something like transition to superrotation or any of these other nonlinear effects that you see? Could they be different in the real world? Is it possible that we might hit them sooner, or is it more likely that they won't happen at all? Maybe they're created artificially. How do we think about this in the context of GCMs that may not have the ingredients that we need?
Yeah, that's a great question. I wish we had a a fully agreed upon theory for the MJO in particular. I mean, there's still, I mean, you know, there are still schools of thought there, and, you know, still people coming up with new mechanisms that can drive amplification of the MJO and so on. So I guess the main school of thought thinks of the MJO in particular. I'm focusing on the MJO in particular because that seems to be the key player in at least the simulations that I was showing. So I guess the main school of thought sees the MJO as being intrinsically tied to moist processes and arising from an instability, I guess, due to the convergence of moist static energy into the warm column. So a little bit like Caroline was discussing for aggregation. So it's kind of a big scale aggregation in some sense. We did some work trying to figure out if the increase in amplitude in the MJO that we see in our simulations was linked, you know, how, to what extent we could explain it as a change in these kind of taking this moisture budget approach. And it was, the answer was not very clear, actually. I am tending to think that there's promise in the idea that this Kelvin-Rossby instability, which is actually a dry instability, could play a role, and that would be very interesting. And the one way in which you can trigger this instability, in order to have this instability, you need a strong subtropical jet. Okay, so you need the subtropical jet to be particularly strong, and the intensity of the subtropical jet is controlled to a large extent by the intensity of mid-latitude eddies. As you go into a warmer climate, the mid-latitude eddies tend to move poleward and get weaker, okay? And so that actually tends to strengthen the mid-latitude, well, the subtropical jet, and that can favor the onset of Kelvin-Rossby instability, okay? So that is interesting. It could go that way, and it's possible that the Kelvin-Rossby instability itself plays a role even in the modern climate in triggering the MJO. So anyway, these are all open questions and to which I don't have an answer. I would say that certainly the fact that we don't represent the, you know, the smaller scales and the convective aggregation and so on, either in the tropics or in the mid-latitude, is going to play a role in, you know, so if it's true the MJO is really linked to, you know, things occurring at the convective scale, and we're not resolving that properly, then the behavior of the MJO when you fully resolve it is, and go to higher temperatures, is, you know, could be very different to what we see in GCMs. So I'm really looking forward to seeing what happens in these, you know, 1 kilometer global runs with very high CO2. On the other hand, you know, the mid-latitude eddies could behave rather differently also if you don't resolve these small-scale processes, and that could lead to. So there are, I can see many possibilities for a transition to superrotation occurring even at lower CO2 and lower temperatures than we need to use in these simulations that I was showing you.
Okay, that's fascinating. Caroline, do you want to jump in? Yeah, sorry.
Sorry. No, just I think the link with the clouds is really very intriguing, very fascinating. And I mean, the work of Tapio, where the low clouds, Tapio Schneider, the low clouds disappear. This is something also that tends to occur in simplified models. And you tend to have more bifurcations, more multiple equilibria, more hysteresis. And when you complexify the model, you have a full climate model, those things tend to not occur anymore. And I think that's several conclusions must be drawn from it. First, we need a hierarchy of models. Whatever we do, we need to make sure that it occurs in a wide range of models, from little, you know, mathematical model to the full model, low or high resolution. And also, whenever we find a phenomenon like this in idealized simulations, it's really important to assess how it may project on in more complex situations. So, but I think the link with the clouds is really, really intriguing. It could be extremely important, actually.
Yeah, this wouldn't be the first tipping point in the series that comes out more extreme in simple models than in a more complicated one.
Exactly.
That's
Exactly.
a frequent,
Absolutely.
frequent situation. I'm going to go to some of the questions in the Q&A. There's one here from Aswathi saying, long wave cooling is explained one of the mechanisms for aggregation of clouds, but it's the same mechanism at which thickness of marine stratocumulus increases at night. So the question is, how do you distinguish between cloud feedbacks which increase cloud amount versus self-aggregation, or are they the same?
Sorry, so I was trying to find the question. Long wave. Oh, I see. As what?
It's basically asking maybe how cloud amount is related to aggregation. That might be something that you said.
Yeah, no, that's a good question. Yes. Yeah, exactly. So the long wave cooling in the aggregation case is in the dry region, so in the cloud-free region, and that's what's tending to cluster the clouds. For those low clouds, the long wave cooling is at the top of clouds, if I understand this well, and so it's in the cloud region. And so that's something different, and it's a very important mechanism, and it's been identified in more like marine stratocumulus, as the person says. For aggregation, I think one thing also that we learned from it, from those idealized studies, is that when we study clouds, we should not just look at clouds. We have to look at what's in between clouds, the outside, because it's a closed system. What goes up goes down, right? So the dry environment also matters. And this is where the long wave cooling for aggregation matters. And yeah. I should keep it short probably, but I had a story on this because we went on a cloud campaign and actually we flew in clear air, and the people who had those measurements of microphysics, they were going nuts because they wanted to see clouds, but we were, you know, it's hard. It takes time to explain that we also need measurements outside of clouds. It's super important, I think.
Yeah, definitely. Okay, there's a couple of questions on land and what the land surface has to do. Actually, one of them asked about Cordex, which is focusing on regional land simulations. And the other one's asking about how the land surface might affect the phenomena you're talking about. And we could probably add to that the fact that we all live on the land. And so are there impacts on the land surface that any of these changes specifically might have if they were to occur? So I can send that question to both of you. Whoever wants to jump in first, go ahead.
You want to take this one? I go.
All right, Caroline, you go.
Okay. Sorry. For the land, so the interaction with the surface, it impacts quantitatively the aggregation process, the timescale. Not really qualitatively. It still occurs. So you can either play with an ocean surface with heterogeneous SST. This was, in fact, Sarah Shamek's PhD, and then you get more easily aggregation. Those aggregations are for really homogeneous conditions. As soon as you put heterogeneity, you will help those feedbacks because it tends to help concentrating convection where it's moist or warm. Now, if you have a limitation of water, so if you're over land and it's quite desertic, it can actually slow down the aggregation. So it interacts with the quantitative properties, but it doesn't stop aggregation from occurring. And now for the impact, one of the big impacts is on precipitation extremes. And I think I saw Jaiwa in the list of participants. He's had a recent study on this where Steve, you've worked on this too. If you aggregate more convection, you tend to have stronger extremes, not just because convection stays there longer, so you accumulate rain. So if you look at daily precipitation, it's also enhanced, but also instantaneous rates, because the atmosphere is more humid, you have less evaporation of rain, and so the precipitation efficiency, the amount of precipitation you get per condensation rate, is larger. And so all this tends to lead to much larger precipitation extremes, which has obvious consequences.
Rodrigo, did you want to jump in?
I think the specific questions asked there were more about the how aggregation were more directed to you, I think, Caroline, about how aggregation is affected by.
Well, I would be wondering, so if we had the thing that happened in CAM, how did that affect the land surface? Does it affect precipitation differently on land or ocean, or could it be disturbed by I mean, there's land in your model, so
Yeah, yeah, that's so.
And so I was thinking the permanent El Nino could have impacts on tropical cyclone genesis and how many arrive in Southeast Asia, no?
Yeah, that's an interesting one. Yeah, actually, if you get into a superrotating state, you would have a really sheared, because the superrotation only happens in the upper atmosphere, or in the upper troposphere, and you still have easterlies near the surface. And so you would have a really sheared wind profile in the tropics. And so probably cyclones would go away, actually. Of course, that model doesn't resolve tropical cyclones. But that's another thing that I would be interested to look at if one of these high resolution simulations actually does exhibit superrotation. So you would be in a paradoxical situation in which, you know, you have super warm SSTs, because the SSTs in the simulations are 35 degrees, tropical equatorial SSTs, and very few cyclones. Maybe the tropical cyclones that did manage to form would be super strong, but yeah. There's also, going back to the issue of how land affects things, one important role that land has is that it gets very hot in the summer and, you know, cold in the winter. So it drives strong seasonality, and it drives, you know, a strong seasonal asymmetry in the Hadley cell strength. And this seasonal asymmetry has a really, so the fact that you have you know, during the solstitial season, when you have, you know, summer in one hemisphere and winter in the other one, you have a Hadley cell that actually spans the equator, right? So it rises in the summer hemisphere and subsides in the winter hemisphere. And this cross-equatorial flow has a really strong damping effect on equatorial wind. That's actually the main reason why we don't have superrotation on Earth, even though there are tropical waves on Earth that could, you know, are trying to drive superrotation, right? But in the annual mean, we don't have it because of this seasonality. Now, if you look at certain seasons, there actually is superrotation even today, even on Earth, right? So, you know, and if you look at particular sectors, then, you know, in particular over the Western Pacific, there are westerlies, right, on the equator. So, so land can be important in that sense. The distribution of land and the temperature, I guess, you know, land cover could affect the temperatures that you have and so on. So that can be important in controlling superrotation.
Okay. So does that mean certain seasons could see this, could be more sensitive than others to this change?
Yeah, there's actually a strong, yeah. So I've really only been talking about annual mean superrotation, but there's a really strong seasonality, even in all the simulations I've showed you. There's a really strong seasonality in the superrotation, and that seasonality depends very much on the distribution of land. So in aquaplanet, you know, there's very weak seasonality, and in the simulations that have continents, it's the seasonality is much stronger. And in particular, when you use modern conditions in which we still have ice caps on Antarctica and so on, even at 5,000 ppm, you know, which is not realistic, but anyway, you get really strong seasonality. With the Eocene configuration, it's weaker.
Okay. Well, I'm still encouraging more questions in the chat, but while we wait for any more to show up, one more for me. There are a few people now, some who are on this call, I think I saw Tim Lenton earlier, who are really interested in the early detection of tipping points, if you're approaching one. Now, maybe this isn't a tipping point, so there's no early detection, but I just thought I'd throw the question out anyway. If you see anything in your model simulations that might give you a clue as to what an early phenomenon change might be that might indicate that something in the atmosphere is changing.
I think typically people look at variance increases. It's a little vague as a response, I guess, but you would look at how the variance changes. So typically, if you're closer to a bifurcation point, you tend to have more larger excursions.
Yeah.
I mean, has the aggregation, I mean, is aggregation related to, can it be seen as a tipping point in some sense? Have people seen it, can you transition from an aggregated to a non-aggregated state
You
with the
can.
same parameter?
Yeah, you can. So we did some experiments like this where you change the temperature. So as we said, it's favored at warm. It tends to be favored at warm temperatures, at least in the model I'm using. It's favored at warmer temperatures. So you can increase the temperature, then you have more aggregation, then you decrease temperature, and you can have hysteresis. It can be sticky, or you can disaggregate after a while. So you can have such things. I don't think it has been fully studied, but you can have things like this.
So marine stratus are a tipping system, right? Because they develop holes. If rain gets going, it washes out CCN, inhibits cloud formation, you end up with a hole, you end up with a hole that has small clouds that are raining, and then around it you have high cloud cover that's not raining. So we already do have tipping systems, and even rain from a storm. Clouds are a tipping system in any case. You get above a critical rain threshold and critical water mixing ratio threshold, and you get rain. So I guess the question is, does this scale up in some way?
Yeah. Yeah.
I mean,
also, there's another question I have is, I mean, do you think the aggregation scales up to sort of NJO type scales? I mean, can you think of, I guess that's a question that many people have asked.
Yeah. So physically, yes. I mean, it depends how you define self-aggregation. Here I put forward more the mesoscales, but if you think of it as any of those feedbacks that helps organize convection, people have looked at it in terms of the impact on the MJO or the ITCZ. In fact, there's, I think, a branch of the community who thinks it's mainly relevant for the large-scale organization more than mesoscale, because at mesoscale you have so many other things going on. And for the MJO, there are, I mean, you need surface flux feedbacks to propagate it, but those radiative feedbacks are important for the onset of the MJO, at least in some idealized studies. It's always the same question, how relevant is that to the real world? And we're working on it really hard. We'll know soon. But there are hints that it could be important for the MJO. Yeah, and then for the tipping point, I mean, I don't know if it's tipping point, but more like a threshold thing, like tropical cyclones are, I think, an example of an organization system that goes bananas, right? Like it's not, I mean, for a long time, people studied tropical cyclones using linear theory, linear perturbation theory. So they say, imagine you have some cloud distribution and then you put a little bit of a perturbation, does it grow into a tropical cyclone? And this is how they explained it. But if this was true, we would have tropical cyclones all the time. And it's not true. It's because it's not just linear perturbation, but you have a threshold. It's like, if you have a little bit of organization, you come down, it's sort of conditionally stable, meaning that it's unstable under the condition that you reach a certain threshold. So once your low pressure system or perturbation is large enough, then it can degenerate into a tropical or amplify into a tropical cyclone.
Yeah.
Okay.
Well, to answer your question about how do you early detection and so on for superrotation, I guess you would see longer and longer period, because on Earth we do have in certain seasons, certain sectors, you do see superrotation. So westerlies on the equator, so you would see longer and longer periods or stronger and stronger such events, increasing. So that maybe there's. Yeah, I don't think anyone's looked at that actually. Maybe you have, Steve. You have a.
No, but sounds like a good idea. Okay, our homework is to start looking at trends in the persistence of upper tropospheric winds. Well, since we don't have any more questions, I think I might wrap this up. Last minute, if anybody listening wants to suggest new topics for future events, please tap those in to either the chat or the Q&A. That'll all get saved. Oh, there's a last minute question coming in. Maybe I'll just throw this one in here. Maxime asks, what's the importance in percentage, he's asking for a number here, of cold pools and self-aggregation compared to entrainment radiation and waves? There's a real short answer question.
Well, Maxime asked hard questions.
Yeah.
I mean, in the real world, in the real world, we don't know. And that's why actually we wanted to have this review of theoretical models, because at this point, we understand aggregation well enough to write equations for it. And so we have things that we can go in the observations and measure. So we can measure the radiative feedback. We can measure the couple. And if we know which aspects of radiation, which aspects of feedback matter for aggregation, we can quantify this using this fundamental understanding that we've gained in the past decade. So in terms of percentage in observations, we don't know, but I think we're at the stage where we can use those idealized models to compare to observations, because again, climate models can be used. We could use the diamond simulations or NextGen. But in terms of the literature on aggregation, I think the radiative feedback is the leading one in terms of aggregation.
Okay, so it sounds like in addition to monitoring upper tropospheric winds, the other thing we need is global cloud resolving models. All right, I think I'll wrap this up now and like to thank both speakers again for wonderful talks and lively discussion. So thanks very much for joining us. Our next event is going to be on health implications of climate tipping points. That's going to be on December 5th. You can register at the link online or find it on the website mentioned earlier. And the recording of this event will be, like all the others, available within a few days afterward. So thank you very much for signing in, and we'll see you next time.
Thank you.
Thank you. Bye.
Bye. Bye, Rodrigo. Bye, Steve.
Bye.
Bye.